Poor elevator service often leads to long waits, long queues, crowded cabins, and denied boarding during peak periods. This links us to our problem statement. How might we help lift management optimize lift operations by reducing average waiting time and queue length? Our simulation visualizes how different lift control strategies perform, taking into account real-world constraints like capacity, rush hour demand, and disruptions to identify strategies that improve efficiency and service quality. The key stakeholders for this elevator simulation are elevator companies, property managers and operators, building owners, operations research analysts, and the student and staff who use the elevators daily. Together, these groups are involved in improving lift performance, from designing better control strategies and managing operations to making investment decisions and experiencing the quality of service firsthand.
Model. It starts with student generation by exponential distribution using our data. Destination is also generated by probabilities using the data we collected. After that, the student is assigned a floor with a floor value, and also the graphics are changed to the specific floor. They then go through a branch which assigns them to their starting floor based on the probability as well using our data. After that, they go to the wait queue at every floor and they wait for the lift. So at this queue, two scenarios can occur. The first is that the lift comes. When the lift comes at board, they board the lift and then they follow the lift until it reaches the destination before they leave, where they alight and leave the system. The second scenario is when they wait too long in the queue, which is set for 2 minutes in this simulation, and they go to the Renergy queue. So this Renergy queue will show the percentage of how many passengers actually left the queue. We also will be able to see the average waiting time of the queue from here based on the queue numbers that are shown by the queue length. The elevator will then go from floor to floor, alighting first for all the passengers before boarding new passengers. Can adjust a few parameters in our model. The first thing that they can do is to generate more lifts. They can go to the lift generation and change this max number to have as many lifts as they desire. They can also change the boarding and alighting times based on the service time. We set it here as 1.5. They can also change the capacity of the lift. We have set it to 16, but they can increase or decrease based on the size of the lift that they have. They can also change the Renergy queue length, so the time that it takes that people are willing to wait, we have set it to 2 minutes. They can adjust it as well. They can also adjust the starting distributions. They can adjust the exponential mean over here. They can adjust the discrete distribution. We have the probabilities of them choosing floors 1 to 8 depending on the location. They also can decide
The performance indicators chosen for output analysis are the average waiting time and queue length. The parameters chosen as part of our sensitivity analysis are the boarding time, alighting time, traveling time, number of lifts, and waiting threshold. Firstly, by keeping the waiting threshold constant while varying all other parameters, we found that mechanical efficiency of lift has lesser impact as waiting threshold decreases. Subsequently, by keeping the lift count constant and varying all other parameters, mechanical efficiency yields proportional reduction of wait times. Further observation shows that at the lowest threshold, maximum mechanical efficiency determines whether all passengers board the lift. In a highly efficient system scenario, there is stochastic anomaly where the average waiting time was no longer controlled by mechanical efficiency but by the random luck. The limitation of our model is that it follows a loop movement. This means that the elevator will not directly travel to the floor with immediate demand, but will make a loop through all the upper floors before going back down. In reality, elevators use targeted movement to prioritize floors based on an active cause. So in conclusion, faster cycle times significantly reduce both wait times and queue attrition, provided mechanical speeds are accurately modeled. At the same time, system performance is highly sensitive to the waiting threshold. Varying passenger patience levels, this drastically changes all the key performance indicators.